Thanks very much, Stephanie. And a big thank you for organizing this event and inviting us to this talk. My name is Mahesh Venkataraman. I am the Chief Technology Officer at 1414 Degrees. And I've been tasked with describing our technology, why we exist, what are the markets that we cater to, and what is the problem that we're trying to solve, all within the next 20 minutes. So hope you enjoyed the talk. So I'll first give you a brief overview of our company. We're an Adelaide-based, publicly listed company. Our focus is on thermal energy storage systems, and the target markets are the very hard-to-abate heavy industry sector. We're talking the steel industry, cement, alumina, hydrogen, and ammonia production for fertilizer. All of those industries require very high temperature heat, and our vision is to decarbonize these heavy industries using renewables. Our major funding partners are Woodside, and production partners being Refertechnik in Germany. And we have a specialist R&D platform for optimizing the storage media and the low-cost silicon technology. So the problem we're trying to solve is the high temperature heat. The pie chart I have over here shows the total global final energy consumption. It's of the order of 400 exajoules. About a third of that is used in the industries, and a large share of that is right now used for heat, and a lot of it is actually just from fossil fuels. Now, the dark orange bar you see over here, this is the high temperature heat usage above 500 degrees Celsius, which is a substantial share of the heat market. And the energy transition, that's not just about decarbonizing the transport and the electricity sectors. We need a clean energy solution that can cater to the high temperature heat market as well. There's a massive gap in this process heat market. Right now, there are no commercial options which can be an alternative to the fossil fuels, especially when you're talking above 500 to 600 degrees Celsius. So what's our solution to this problem? We've designed a product called SiBrick. It is our core silicon technology. It's a phase change storage material, and it harnesses the capabilities of pure silicon or a silicon-based alloy to store the heat from renewable electricity. The purpose of any storage is to smooth the intermittent generation and provide that energy on demand. And that's where, when you're designing a system, you have to look at certain aspects such as the energy storage density, because that has an impact on the loss rate from the system. And the higher the energy storage density, the better it is for most of the plants. So what we've compared over here is the operational temperature on the y-axis and some of the sensible and latent heat storage media that are being researched and developed by other people. And the area of these bubbles is proportional to the total amount of energy that is usable energy stored in the bricks. And you can see the SiBrick can actually store about 2 to 3 times more than some of the conventional storage solutions that are being looked at. Now, this red portion in the middle is the latent portion of the total stored energy. So what latent energy means is that when the phase transition happens, it requires a certain amount of energy. And you can use that phase transition to store the energy and recover it when it is required. So about 55 to 60% of our total stored energy is actually in that latent phase. So we can actually cycle between a smaller delta T and still be able to store a very large amount of energy. So for reference, the bricks themselves can store up to 600 kilowatt hours per meter cube. And this is not from ambient. This is the usable energy at temperature 900 degrees Celsius output. So the SiBrick is used in a thermal energy storage system, and that system, we call it the SiBox. Basically, the SiBox takes in any sort of a renewable generation. It could be electric input, it could be biogas, could be some other form of energy as well. In this particular graphic, I've shown an electrical resistive heating element, which converts that electricity to heat. The heat is stored in the bricks, and then when it is required, the energy is recovered through a heat transfer fluid. In our case, we use air as a heat transfer fluid, and the outlet hot air can be used for different applications. Because it is at such a high temperature, up to 1,000 degrees theoretically, you can actually use it for power generation, manufacturing processes such as alumina, glass, steel, pulp and paper, excuse me, and even in the aluminium industry and pyrolysis, etc. So these are some of the projects that we've done over the years. Our beginnings were actually in a research lab back in 2008. The first prototype for the concept with pure silicon was developed in 2016. It was coupled with a Stirling engine to convert that output heat into electricity, and this was a 30 kilowatt electric output system. The next iteration was a thermal energy storage system for the industries called TESIND. This was about 5 years ago. The box capacity was 6 megawatt hour thermal, and it was coupled to externally fired gas turbine, and it was generating 180 kilowatts of electricity output at the design point. Now, this same unit was then actually installed at a wastewater treatment facility at Glenelg in South Australia. The input was changed from electricity to biogas. It was a wastewater treatment facility which converted the sewage sludge, municipal waste, etc., to biogas using anaerobic digestion, and then the energy was stored in the gas test. And then when the price of electricity on the grid was high, it was sold back to the electricity grid. The energy conversion system was again the same, externally fired gas turbine, 180 kilowatts. But those were the previous generations of our technology. We've worked in the last 4 to 5 years on the scalability of the thermal storage media, and thus the Cybox module was born. This is the latest iteration of the technology. We've installed that in our facility in Adelaide, and the capacity is 1 megawatt hour thermal output. The phase change material used in here is not pure silicon, it's an alloy of silicon, but still very high temperature, and on an energy basis, it is equivalent to silicon. I'll show you some results from this Cybox demonstration module, as we've been running this for the past 6 to 8 months continuously. But first, I'll just like to explain where these Cybricks and the Cybox can be used, what sort of systems can you design around these bricks. So it's a mass manufacturable energy solution. These are in a brick form factor. They just look like a regular refractory brick on the outside, and there's phase change going on the inside. So it can be used in a latent heat battery, that is the Cybox system. So it's a natural gas replacement. So you can deliver hot air from clean energy source to any industrial process, and we can run these boxes 24/7, even with intermittent power, and I'll show you some results showing that. It can also be used for these next generation electrical reactors. So if you want to convert any of the current processes to an electrified version, then having an integrated storage inside these reactors can be quite good, because you can reduce the losses. There's no additional heat exchange going on. Hence, you can achieve very high efficiencies because of that. And that can be used in many of the catalytic conversion processes for production of clean hydrogen. It could be for calcination in the cement industry or alumina. So those are the reactors we're working on with different partners. It can also be used for waste heat utilization if you have a source of heat which is high enough temperature and high quality heat. An example would be the glass industry, where you use regenerative furnaces, which are natural gas fired. But the key issue in those furnaces is the temperature variability inside the furnace, and it's hard to control. You can use the Cybricks as a very high thermal mass inside the regenerators and stabilize that temperature output as well. So I'll show you some results from the demonstration module. This was commissioned in June of last year, and since then we've been running the box continuously. And these are the actual results from the box, not model results. These are experimental results. So from the same box, you can actually set the outlet temperature anywhere between 600 degrees to 900 degrees. And depending on the outlet temperature, you get different hours of storage because of how much you can cycle the box. So at 700 degrees, for instance, you can get about 15 hours of storage. And at 900, it's about 6 hours of storage. And you would notice that the outlet temperature is very, very stable. In fact, we can control this temperature within plus minus 2 degrees for the entire duration of the discharge. So that's one mode where you can use the storage for arbitrage on the grid or providing during peak pricing periods. This result shows the reproducibility of the results. So this is a 30-cycle run over a period of 1 month. Outlet temperature being 850 degrees. The gray bars are the discharge periods, and the light colored bars are the period when the system is charging and held for a period of time. So each of these runs are about 8 hours of discharge, and you can see the reproducibility in the outlet temperature that you can achieve. Another mode that we have demonstrated from the box is doing a constant temperature output. So in this mode, because the charging and the discharging are completely decoupled from each other, you can do multiple cycles in a day. You can charge the system while it is dispatching without disrupting the outlet. So the bottommost plot shows the outlet temperature over a period of 6 days, continuous heat output at 700 degrees Celsius. We've done this at higher temperatures as well. And the state of the charge inside the storage system is shown on the top bar. The unique thing about this is that the control system basically selects the period of low prices on the grid. The blue curve over here is the actual electricity price, spot market price on the grid in South Australia during these periods. And you can see that it charges during the low price period. In fact, some of these prices are negative price events. It happens quite regularly in South Australia. South Australia has one of the highest renewable penetration in the entire world. We're about 70% penetration of renewables on an average throughout the year. So hence why we do get a lot of fluctuation in our electricity prices on the spot market. So we have the capability to utilize the low price periods. Typically, this is when the renewable generation is quite high, and charge the system and then deliver the output continuously. Just on that renewables remark, this is another test that we did with a combined solar plus wind generation profile. So the orange ones are the solar profile and the blue one is the wind profile. And just using the renewable profile, the system charges and maintains its state of charge such that you can deliver a constant high temperature output from the box. This is a 5-day continuous run, which we finished quite recently. The wind and the solar profiles are based on the actual generation of the South Australian national electricity market. It's not location specific, but for the entire state. So where can this technology be used? So I'm going to run through very quickly a couple of case studies. I won't go into too much detail, but the direct reduced iron process is one of the most up and coming and expectedly a huge growth market in the next decade. The conventional way of iron and steel making is the blast furnace route, which contributes about 7% of the global CO2 emissions, right? And DRI can be a much more lower emissions intensive route. The conventional way of doing a DRI would be using natural gas, which is reformed inside a reforming reactor, and the reducing gas is then passed through a shaft furnace. And the energy required to drive this reforming reactor could be of the order of 30 to 35% of the lower heating value of the natural gas. Now, this process could be run with hydrogen as well, but in case of hydrogen, you still need to preheat the hydrogen which enters the shaft furnace. And the heat load for this can be actually about between 10 to 25% of the total hydrogen usage for the reduction. So it's a quite a big heat need, and providing the heat using hydrogen, which is a high value fuel, can be quite inefficient. You could use direct electricity as well, but then coupling it with an intermittent renewable source becomes quite difficult. And that's where the Cybox comes into the picture. You can replace the natural gas in the conventional reforming DRI system, and you can do the preheating of the gases using the Cybox again. This can lead to about 30% reduction in the natural gas usage in one case, and roughly about 25% of the hydrogen usage in the other case per million ton of DRI produced. So the other process we've looked at is the Bayes alumina process. Again, the calcination step in the alumina production. This is not aluminium production. This is alumina. Bauxite to alumina conversion is a very high energy intensive process. It's done through the Bayes route, and currently the fuel that is used is either coal or natural gas. And there is a huge steam requirement as well for the digestion step in the Bayes alumina process. So basically we can replace 100% of the natural gas usage in the steam circuit and up to about 35% of the fuel usage in the Bayes calcination circuit. So in total, about 70% of the total natural gas usage in the fossil fuel usage in the alumina plant can be replaced with a heat from Cybox. We've looked at many other use cases as well, one of them being the cement industry. There's also bridge stabilization. So the value of energy that is used by these industries is of the order of hundreds of billions of dollars. And there's a big need for long duration energy storage, especially in these target markets. So what I've shown over here is the total addressable market that we have for the Cybox. This is split, the total process heat from the fossil fuels is of the order of 20 million gigawatt hours. I've split that in different temperature bands. The very low temperature need, about 100 degrees Celsius or lower, is about 25% of the market. And then another 30 to 40% of the market is in the greater than 1,000 degrees Celsius route. But in the middle is about 50% of the market, which is quite a big market, and especially the 500 to 1,000 degrees Celsius market. Cybox has a very big competitive advantage because there's probably only very few companies globally who can provide that high quality heat. So the commercialization pathway for us is that we're at this point right now doing the demonstration with the Cybox module. I've shown you some results from the Cybox demonstration module. The next step for us is a commercial scale pilot of the order of 10 to 100 megawatt hour. We are actively speaking with many different heavy industry users on the next large scale commercial installation of the Cybox. And in the next 3 years' time, we want to go to a gigawatt hour scale production. And the pathway for us to get to mass production is collaboration with refractory suppliers. So Refratechnik, who are a German company, one of the largest refractory suppliers in the world, they are a production partner. We're not trying to produce these bricks ourselves because the scale-up journey to these gigawatt-hour scale systems is quite steep. And that's why we want to utilize the existing infrastructure and the existing expertise in the industry to tailor our product to these production plants. And that's how we get into the mass production of these cybricks. That's it from my side. Thank you very much. And I'll be happy to answer any questions that you have.
Okay. Thank you, Mahesh, for the insights. Many thanks. Yes, so I open the stage for the audience. Is there any questions? You can just raise your digital hand or write into the chat. So, okay, so I give the audience a minute to think about, and I will start with a question because I have a couple, but I start first with one. So I was curious about the development of the bricks you showed before. Like it's a compound material, if I got it right.
Something like that.
Okay, I mean, I'm not sure if you can talk about the details first of all, of course.
The exact functioning of those bricks, but on the surface, they would behave just like a refractory brick. The photo I shared was actually a brick which has been cycled inside the furnace for a number of months, and it still looks the same. Okay, because if you have the phase change from the liquid, from a solid to liquid, I would expect to drown the liquid. I guess. Yeah, the containment of the metallic alloy is the key ingredient of our IP, and how to prevent any degradation. Okay, no, very interesting. Nice to see that there's a successful solution. Very nice. So I saw there was Harald. You had a question.
It was basically what you already asked, so I put my hand down. Because I don't want to go to ask for more details because I'm quite sure that you don't like to answer that.
Yeah, I guess that's the problem, that you cannot just share the too many insights of the production and the research. But we have some more questions which maybe are good to answer. So there is one question which says, hi, great presentation, first of all, to you. And what is the percentage heat loss per day through the box?
So heat loss per day. Okay. So let's assume 1 cycle per day and you're operating at about 900-degree outlet temperature. The heat loss is basically scaled with the size of the system. Right? If you're operating on a very, very small scale, like 1 to 2 megawatt-hour scale, the losses will obviously be higher. But when you get to a reasonable scale, say 100 megawatt-hour sort of scale, you expect the efficiency, round-trip efficiency over the course of a full day to be of the order of 90% or more. And this includes the electrical losses in the heating element controllers, and then heat losses from the box as well.
Okay, thank you. So there would be one follow-up question which fits quite well. So which I would like to ask maybe as last question, and then we can move on. It asks, which insulation do you use for the box?
Well, insulation design itself, I wouldn't disclose too much, but it's a multi-layered insulation, just like a lot of these more efficient systems. Typically, the inside surface would be a high alumina-based refractory, which would be rated to up to 1600 degrees Celsius. And then as you drop down the temperatures, you get to more efficient insulation, including microporous insulations and the like.
Okay, yeah, many thanks. So we have 2 more questions. Maybe we can answer one quickly, and the other one I would leave open for the chat. So Mahesh, if you want, you can answer in the chat or maybe exchange email addresses. But let's say we have a very last one, which asks, does the silicon alloy form eutectic or non-eutectic PCM?
So the silicon alloy, we work on a lot of different silicon alloys. Some of them are eutectic, some of them are not. The one which is used currently is a eutectic alloy, but there are many different alloys we use in different temperature ranges as well. I can answer quickly the last one as well, which is about the heat transfer to the bricks. So during the charging, the heating side, it's usually radiative heat transfer at those temperatures, and we're using air as a heat transfer fluid. So on the heat extraction side, it's mostly convective and a bit radiative.
Okay, so thank you very much for answering all the questions. As I said, maybe if there are some more questions, just write into the chat or you can exchange your details. Yes, many thanks again. I would also have a lot of questions, but it's not enough time now. But I'm also looking very much forward to hear the talk from Russell. So Russell, the stage now is yours.
Excellent. Thanks, Stephanie. And yeah, thanks everybody for turning out. All right, let me get everything set up here. All right, Stephanie, does everything look good?
Yes, looks very good.
Perfect. Yeah, so like Stephanie said, I'm Russell Goldfarbmuren, and I'm the co-founder of Rebound Technologies. And you know, we started the company in 2012, and the goal of starting Rebound was really energy storage from the very beginning. We came from an energy storage background, but we realized, you know, kind of right out of the gate that especially in a behind the meter setting, it's very challenging to get these systems to pay for themselves. It's very challenging to get customers excited, you know, when they're operating their own business, to, you know, kind of distract them and talk about energy storage, which they might not understand. And so what we wanted to do was create a product that would get energy storage onto the grid by selling primarily value add to the customer to increase their operational effectiveness, to increase their bottom line revenue, and use that to drive sales of grid storage. And so that would allow us to work outside of the context of government incentives or utility programs that are kind of traditionally pretty slow. And it would allow us to scale really rapidly to hit really large storage goals and really big carbon offsets. So what we do is we make a thermal battery for industrial customers on the low temperature side. So for cold chain facilities, and we take those facilities and we turn them into grid managed thermal batteries. And we do that by selling them a superior refrigeration product. So IcePoint is the name of that product. And I'll get into, you know, the technical side of things of what's happening inside this box, but it's really important to understand before we get there, you know, what are we actually selling to the customer? Because that drives our whole technical development. So primarily what we're interested in is selling grid batteries. And I think that's kind of what everybody on this call is interested in, but the customer isn't actually that interested in that. And they don't really understand the need for that on a you know, bottom line kind of standpoint. And so what we're selling them is primarily the number one value that we're selling them is this industrial freezer. So we sell a superior industrial freezing product, and we do that through what we call agile cooling. So in these facilities, you have food processors, you have cold stores that are doing blast freezing, and they have really transient loads. So that just means that their loads are, you know, going way up, way down, you know, by a factor of 3 to 5 on a pretty regular basis throughout the day. And traditional vapor compression systems have a lot of trouble serving that load. And so what happens is you oversize the vapor compression system, and then that represents a really wasteful CapEx, because that product gets utilized at a pretty low level. So some of these facilities are running at 50 to 60% utilization of their assets, which for a cold storage operator, that's obviously not the optimum. So we can come in and we can offer a product that can match their load a lot better and give them just much higher quality low temperature refrigeration. And so that's the primary driver of why someone would want to put this at their facility. A secondary driver that the customer is also really interested in is this desiccant property of our system. So we use brine and ice as our refrigerants, which again, I'll get to later. But what that allows us to do is we simultaneously provide cooling and moisture management. And so at facilities throughout the cold chain, moisture control is really important. So not only important for product quality, but for worker safety and for efficiency. So we can come in and we can simultaneously cool and dry their air. And we do that at a much higher efficiency than traditional desiccant systems because first, the scale of our technology is much higher because our refrigerant is water. We're already processing so much water that processing a bit more water, we can do much more efficiently. And then secondly, we're not over drying the air or over concentrating our brine. And so we kind of, this is a technical group, so I'll use the phrase psychometrics, but we kind of walk down the most efficient psychometric path to deliver that moisture control. And then finally, the most important thing to us is this grid battery aspect of our technology. It's the least important thing to the customer, but we're able to, at the point of sale, really have a conversation that is driven by these first two items that drives 80 to 90% of the value proposition, and then the remaining 10 to 20% is the ability to arbitrage time of use rates to avoid demand charges. And that conversation is much more about the additional cost of adding more storage. So the system basically comes with 3 hours of storage for free. That's what we need to just provide these two initial value streams. And then the grid battery part of it rides along at only the cost of adding more storage. So if we want to add 6 hours of storage to arbitrage time of use rates, that comes at a very low cost because we only have to make our fiberglass insulated tank a little bit bigger. And so that will allow a 1 to 2 year payback on that storage component. And so I'm talking a lot about the business case here and the value proposition, but it really echoes why we developed the technology we developed, because we wanted these sales to be based on bottom line revenue and based on things the customer really cared about and really understood, and not about grid storage or about renewables penetration or all these things that are, a customer might say they care about, but at the end of the day, they're not making, their purchasing decisions based on. So what's really inside that box is a new thermodynamic cycle that we patented back in 2012, and it's been called a lot of things since then. We call it a freeze point suppression cycle. It's also been called a freeze point depression cycle. It's also been called an ionocaloric cycle. It's all the same family of thermodynamics. And the way that it works is if you map it to like a temperature entropy diagram, it looks just like a vapor compression cycle or any other heat pump cycle. And so I'll walk you through the states and the steps here. So you take first your pure refrigerant. In our case, that's just water, and you freeze it. That's analogous to the condensing step of a vapor compression cycle. So that rejects heat to ambient, or in our case, to our top cycle, which then rejects it to ambient. So you freeze the water. So that happens at 32F or 0 Celsius. That produces pure ice. You then mix that pure ice with a concentrated brine, and that lowers the freezing point. That's analogous to an expansion step in a vapor compression cycle, and it produces cold ice and brine. And that cooling is spontaneous, and the energy there is going into the ice, and some of the ice melts. So that's exactly analogous to when you make ice cream in one of those old-fashioned crank ice makers, you put salt in with the ice to get it colder than freezing. So it's a spontaneous process, just like an expansion of a refrigerant. And then that allows you to melt the rest of the ice at a very low temperature, so minus 25F or colder. That removes heat from the refrigerated space. And so that provides your refrigeration load, and it results in a dilute brine that you then need to kind of regenerate. So we send that to a separation process that produces concentrated brine and pure water. And so that's analogous to the compression step. That's where we're doing our work. And that produces a complete cycle that goes around and around and around. And so the key to this cycle is not that it fundamentally can be more efficient, or it fundamentally can be lower cost, or any of those things. I mean, there's arguments to be made that can happen, but the real key is that at every step of the way here, our four kind of materials are pure water at ambient pressure, pure ice at ambient pressure, cold ice and brine at ambient pressure, and dilute brine at ambient pressure. And I say ambient pressure because you'll note those four things are all really easy to store. So the point of creating this cycle was to create a inherently storable heat pump. And that allows us to, at any step along this process, use plastic or fiberglass insulated vessels to store our refrigerant in whatever state we choose. So that lets us then, going back to the actual product, that allows us to store energy for the grid. It allows us to store potential cooling for the customer. It allows us to ramp up our cooling loads to deliver bursts of cooling. And this architecture, we chose to take it into the low temperature refrigeration space, as we thought that was the best go-to-market for this technology. But it's not limited to that. So just like a vapor compression cycle or any other heat pump architecture, we can take this cycle and we can change the refrigerant, change the freeze point suppressant, and we can pump heat, supply process heat. We can go down to cryogenic temperatures, and or anywhere in between. And so just like any heat pump, it really is just about picking the refrigerant that allows you to target whatever temperature range you would like. So kind of where we are as a company, we started in 2012, and we've built a bunch of different prototype systems, pilot systems, systems that use different refrigerants, different freeze point suppressants, and we've this all kind of culminated in last year. In April, we commissioned this first full-scale commercial system in Greeley, Colorado. And this system, the goal here was all about demonstrating the value and the thermodynamics at scale. And so we created this product and ran it and continue to run it. And we really wanted to show we can match the model, we can match the value, and we've really achieved that. So to date, I won't go line by line through these, but we've got quite a bit of operation, quite a bit of demonstration, and just showing that the thermodynamics do continue to work as you scale up, and that we can hit them with equipment that is this big, which was a huge success for us. So I really like to share data. If you follow me on LinkedIn, I post a lot of data there, and I'm really pro kind of transparency, and just talking about how sometimes I talk about how well the system is working and how much of an impact we're having, and sometimes I talk about how much brine is leaking on the floor, you don't run a hardware startup without leaking some brine on the floor. So if you want to see more data, there's definitely a lot up there. But this is one of my favorite kind of data sets we produced. So like I was saying, the system has 3 hours of storage kind of like built in, and then you can add more at a very low cost. Here, what we were trying to show is, despite the fact that we only have 3 hours of storage, we can ride through a much longer period by kind of turning down the system. So here we're supplying cooling, we're consuming power, and this is the peak window here where we drop our power consumption to 0, but we continue to provide not only cooling, which is important, but even more important for the customers, to provide moisture control during a period where you're trying to turn down the system. So the thing that really kind of forces the customer to keep their compressor running 24/7 is that if they don't, that the moisture builds up in their process and causes a lot of problems. So we can provide moisture management throughout a peak period while our system is completely off. And so, that kind of all leads back to, why we started Rebound, why we developed this new thermodynamic cycle, is that, we wanted to realize this cost stack. So, you have the cost of a system to get installed, and that represents all of these purple wedges, all of these components, all of the labor. And then you have the incremental cost of adding 6 hours of storage, and that's only this box. So when you're working with the system and you're getting these systems out into the market, the system is paying for itself because it's delivering these 2 primary values to the customer, which are superior freezing, which we call agile cooling, and moisture management. And that pays for all of these boxes. And then the only thing you have to pay for by arbitraging time of use rates is this much, much smaller box. And so that's how you can get a storage system with a payback of less than 2 years, is by utilizing this much lower cost. And so right now, today, our levelized cost of storage behind the meter, in a diurnal 1 charge a day, 1 discharge a day kind of operation, is $120 a megawatt hour, which is phenomenally low, especially for a first commercial scale. We still have a ton of value engineering and system improvements to implement to drive that down. So our current costs are extremely low for our storage, and obviously they're only going to get lower as we build more and more units. I tried to keep it short and sweet, and I would love I love questions, so please lay them on me.
Yes, so many thanks, Russell. This was a very nice overview. Yes, and I hope your wish come true. So let's see in the audience. Do we have any question? Okay, So again, I will start with one. Oh, no, now we have one. Let's see. Okay, there's one question from Kevin. He says, I noticed that you are working with Lineage Logistics, I hope I said it right, which is, I believe, the largest cold storage company in the world. What are the primary benefits they are excited about?
Yeah, great question. So Lineage is our kind of our anchor customer, and they are the largest cold storage facility in the world, or the largest cold storage facility company in the world. Yeah, they're really the number one thing that gets them excited is this idea that long-term ice point plus vapor compression in a hybrid situation can actually yield the lowest first cost. So here I'll go kind of touch on that really briefly. The idea with agile cooling is if you're in a situation where this curve represents your facility load, serving this kind of, think about it like base load capacity with ammonia vapor compression or CO2 vapor compression is really cost effective. But serving this transient portion is really not very cost effective because you have to size your vapor compression system very large and then use it at a very low utilization. And so you can use ice point to track the transient portions of the load, and you can use vapor compression to serve the base load. So you can think about this like a peaker plant and a base load plant in electrical generation. And so what that does is it actually yields a hybrid system that has the lowest first cost. So instead of talking about storage with a payback, instead of talking about when will this system give you what ROI, the sales decision becomes really straightforward because you're just the lowest and best first cost option. So this is the primary thing that Lineage is most excited about, and really the essence of agile cooling.
Okay, many thanks. Well, I guess it's nice to have such a big partner on your hand for demonstration purpose. I think it's the most important part for new technologies.
Yeah, no, absolutely.
So, as there is not another question, I just will ask one of mine because, of course, I have many again. I don't know. Yeah, one thing is, I was curious. You talked about liquid desiccant as well, if I got it right. Is the brine you are using? Did I understand it right? That this brine is the same brine you are using for the freezing point depression? Okay, and then my follow-up question, because as far as I know, for the liquid desiccant, there are two problems. You can use a brine which is either quite stable, but the carryover might cause some corrosion problems, or you use a brine which is based on organic material, which then might have a problem with the degradation if it's out of a specific temperature concentration range. So do you have any problems with this?
Yeah, no, that's a great question. And the brine that we use is not a secret, not proprietary. We use potassium acetate, and what that allows us to do is, potassium acetate has a really low corrosivity. So unlike lithium chloride or traditional liquid desiccants, potassium acetate is really benign, non-toxic, non-flammable, non-volatile. The key, though, why other systems don't use potassium acetate is when you use a liquid desiccant, in isolation, you have to have a really high concentration because you need to get to those very low dew points using only your brine. So you need to have a desiccant like lithium chloride that you can really concentrate quite high. We don't have that constraint because we're doing this simultaneous cooling and desiccation. So our brine is quite low concentration from a liquid desiccant standpoint, and we don't need to go to those extremely high activities that lithium chloride will get you. So we're able to basically hit the moisture management levels we need at a very low, relatively low concentration, and that allows us to use potassium acetate instead. So and then from a degradation standpoint, yeah, potassium acetate is quite stable. Eventually, I think we calculated it at one point, but I want to say it's like, in 500 years, we will accumulate some amount of acetic acid that will volatilize, it's on the order of hundreds and hundreds of years. So we're pretty good. We should be okay.
Okay, yeah, this sounds good to me. Okay, thanks for your answering. There's another question. Just let me see. So the question is, I imagine your total domestic market is the cooling capacity in the US. What is the total electricity capacity, the potential in the US that can be shifted thanks to this kind of storage? Do you have any data for this?
Yeah. So we look at when we talk about our kind of total addressable market, we do focus on low temperatures, and that kind of goes back to this 800 gigawatt hour value is around what you would get when you address the entire cold chain. So, we tend to say a terawatt hour, plus or minus, just given how much can you really know exactly all the facilities and exactly their loads. But that's assuming, 8-ish hours of storage per facility. If that answers the question.
Okay, thanks a lot. So a lot of potential. There are 2 more questions. Is it okay for you? Are you still in time, or do I?
Yeah. Okay.
Okay, thanks. So we'd go with these 2. One is why the industrial refrigeration with this -25 Fahrenheit over a classical HVAC system.
This is a fantastic question. Oftentimes, people assume that we kind of stumbled into low temperature refrigeration, but we really intentionally targeted low temperature refrigeration instead of HVAC loads. So the issue with HVAC loads is really on the go-to-market. So when you look at the HVAC industry, you have a couple problems. One, there's no kind of consolidated service of HVAC systems. So you have a lot of trouble with maintenance of your equipment. On the flip side, in the cold chain, almost all facilities have on-site maintenance staff already that are already trained to work on our systems. So our technology is not so different from a vapor compression system. It's just pumps and pipes and valves. And so we already have an installed base of people that are ready to work on our systems when they show up at these facilities. The other issue with the HVAC market is you have a lot of split incentives, which means the people who buy the equipment aren't the people who operate the equipment, aren't the people who benefit from operating the equipment. And in the cold storage space, or the cold chain space, you don't have that issue. So our customers are directly the people who make the purchasing decisions and who benefit from the equipment on site. So we really, even though the HVAC market is a little bit bigger, we really very intentionally went after the cold storage market because we thought the go-to-market was actually a lot more appealing for a startup that was trying to kind of crack into that market.
Yes, and there are not many solutions for such cold temperatures.
Yeah.
Okay. Good. Then I would thanks. I would move on to the last question. So, the value proposition seems to depend on a specific need for cooling and the second service. Which industries can it serve? And is it a large share of the cooling energy demand in the industry?
Yeah, so our initial product is really geared towards all cold storage, all food processing, food distribution, and food retail kind of as the last market to be addressed with this product. So that's the order that we're trying to kind of to get into those markets. And that's these values here are just assuming that rollout. But like I was saying, the heat pumping is really I think that the latest value I saw was 4 to 10% of all energy use is going into a heat pump of some kind. And so we really think that our kind of the thermodynamic backbone of our product is going to allow us to address a much wider market. We just believe that it's all about how you move through those markets, right? So we think we're going after the highest value markets first, and then as the technology matures, we'll be able to roll out into really any heat pump or refrigeration market. So that would include commercial cooling, residential cooling, lower temperatures obviously than 1000 C, but up to 100 C heat pumping, even low pressure steam generation. You can do that with a freeze point suppression cycle, obviously with different refrigerants, but because the nature of the cycle is inherently storable, you can convert those loads to flexible demand as well.
Okay, so it seems like then there's a big market to be explored.
Yeah, a lot of work ahead.
Yes, sounds like. Yes, well, that's good. And okay, so considering the time, I will stop here. Maybe if there are questions also, if I may say to the audience, also they can contact you directly.
Certainly.
Perfect. Okay, so yes, thanks again for you two for giving us some insights to your work and for these technologies. I think maybe a couple of me at least I have to digest some parts of the information. And yes, so yeah, thanks again.